Awesome. Thanks, Arpan. And thanks for, everyone inviting me to speak and for organizing this really interesting session. So today I want to dive a little bit further into one aspect of what Lynn just talked about in the previous talk. So this is how machine learning can be used to actually address climate change, both mitigation and adaptation. So before I dive into that, though, I understand that this is, an interdisciplinary audience, some of whom are coming from the machine learning data science side, and some of whom are coming from the climate and sustainability side. So before I actually talk about what it means for machine learning to be used to address climate change, it's probably worth talking about what it means to address climate change in the first place. So I want to talk about that very briefly. So when we talk about addressing climate change, there are a couple of different approaches that we actually mean when we say that. So one of these sort of axes of action is climate science. And this refers to understanding and predicting how the climate will actually change. And within climate science, there are sort of several communities, those that study the Earth, the ocean and the cryosphere, and the atmosphere. But climate science basically refers to, again, asking this question of how is the climate actually going to change? Then when it comes to actually addressing the changing of the climate, so what do we do to, for example, reduce the extent to which the climate changes? Then this is referred to as climate change mitigation. So mitigation refers to efforts to reduce or prevent the emission of greenhouse gas emissions in the atmosphere. And when we talk about climate change mitigation, we need to consider this across many, many different sectors of society. So this figure on the slide is basically showing the sectors from which greenhouse gas emissions came globally in 2019. And what you can see is that there isn't one specific sector that is creating the majority of greenhouse gas emissions. There are emissions coming from energy, transport, buildings, industry, and AFL-U stands for agriculture, forestry, and other land use. But basically, the sources of greenhouse gas emissions are diverse. And as a result, it's important to think when we think about climate change mitigation about how do we reduce greenhouse gas emissions across this wide variety of sectors. In addition, of course, there are efforts to also, of course, pull greenhouse gas emissions from the atmosphere, and that's another aspect here as well. And then the third axis of action here is climate change adaptation. So given that the climate has already changed, we're already experiencing some of these effects, and we're going to continue experiencing some of these effects, how do we respond to those effects that we will face? And this requires both assessing what impacts we think we'll actually face. So there's some ties there with climate science, but also with the social sciences, behavioral sciences, engineering, as we try to assess the effects on our infrastructure, on our human systems, and so forth. And then also then taking local actions at a global scale to actually address those effects that will be felt in different places. And so these three axes of action, climate science, mitigation, and adaptation, are what people tend to mean when they say acting on climate change. In addition to these direct, axes of action, it's also important to consider other frameworks or key considerations to think about when actually pursuing these axes of action. So one of these is climate justice. A related concept is climate equity. And what climate justice and climate equity basically acknowledge is that those who are facing the brunt of the kind of consequences of our changing climate are not necessarily those same parties who actually emitted the bulk of the greenhouse gas emissions that are causing those climate changes. And so it recognizes that basically the approaches that we need to take to climate action need to, first of all, be explicitly cognizant of this in terms of how responsibilities are split, but also that we can't replicate some of the same mistakes in the future of not centering disadvantaged communities in the way that we are actually approaching climate change. So climate justice and climate equity basically say the way in which we actually approach climate change as a whole shouldn't replicate the past patterns of inequity, but instead we have to take equity as a very fundamental consideration in the way that we move forward on climate action. And then another important framework is a co-benefits framework. So of course, this, even though all three speakers so far, we focused largely on climate, this symposium overall is of course on sustainability. And so a co-benefits framework is the terminology that's used to, when we think about climate change and addressing climate change, we need to make sure we explicitly consider the linkages between climate change and the other UN Sustainable Development Goals, which cover sort of economic, social, and environmental sustainability. And again, take those interlinkages very deeply into account when we're actually moving forward on climate action. So this is the really brief overview I wanted to give, just to get some terminology in place about what it actually means to address climate change. And so now when we talk about the role of AI, machine learning, data science in these, we might ask, how does AI, machine learning, data science, how do they interact with these different axes of action? And so Lynn in the previous talk kind of referenced this paper, Tackling Climate Change with Machine Learning, that myself, Lynn, Felix, and several others co-authored. And this paper basically tries to provide an overview and agenda for how machine learning can play a role in climate science, climate change mitigation, climate change adaptation going forward. So for those who are interested in this area, I would definitely encourage you to check out the full paper. And there are also some summaries online that you can use to sort of filter by either climate change related sector or, for example, by the area of machine learning that you work on if you're coming from a machine learning background. And so in that paper, we basically go through many different kind of sectors, right? Different sectors for climate change mitigation, talk about societal adaptation, and we also talk about how AI and machine learning can address policy, individual action, organizational action, these various different kind of cross-cutting frameworks that foster our actual implementation of climate change mitigation and adaptation strategies. And while I won't be able to, in the course of this talk, go into a huge deep dive on every single application in the paper, what I hope to do is give a sense of cross-cutting themes that emerge when we take a higher level look at all of these applications to try to give a sense of the kinds of ways that AI and machine learning can fit in. And so Lynn also referenced this in her talk, but I'm going to be diving into this in slightly more detail. So one of the ways that AI and machine learning are commonly used are distilling raw data into actionable insights. So we've started to see a lot of satellite and aerial imagery becoming available. We've also started to see huge bodies of text documents, for example, policy documents, corporate climate disclosures, where in theory, a person could sit down and analyze these manually, extract various kinds of insights from them. But in practice, the volume of data is such that we're starting to need automated approaches to actually, deal with this large volume of raw data. So some examples here include using satellite imagery to better understand crop cover in agricultural land. So that this image on the slide is from a paper that was basically using satellite imagery to understand sort of, what crops are in particular places, what are the crop yields that we currently see, what do we expect to see in the future, with the goal of kind of informing adaptation strategies in the agricultural sector. And similarly, there are lots of initiatives that are starting to use satellite imagery to try to address some kind of climate change mitigation or adaptation problem. For example, Climate Trace, a coalition of organizations, has used a combination of satellite imagery and other information to try to provide an independent audit of the different emissions that are being produced by different sectors around the world. There are also, and the goal there is to inform international climate change negotiations by providing sort of an open source audit of emissions. There are also initiatives that use satellite imagery to pinpoint deforestation, or to understand where buildings are and what their energy efficiency characteristics are. All of these with an eye on informing usually some kind of policy process that could use that information in order to figure out better energy efficiency policies going forward, or better policies to prevent deforestation or so forth. And then in the text documents realm, again, we're starting to see a lot of policy documents. We're starting to see corporate climate disclosures release these text documents where they have climate relevant information about how a company is addressing climate change or how a particular policy is addressing climate change, but where, again, it's difficult to analyze these things at scale. And so nonprofits like Climate Policy Radar are currently putting forth efforts to actually index a lot of the climate policy documents that exist in the world, with the aim of then using natural language processing and machine learning techniques to actually analyze those and inform how people make policies going forward. And Lynn, for example, has done some work on actually analyzing corporate climate disclosures at scale in order to understand, again, what different companies are doing to act on this issue. So this is one major theme, taking large streams of raw data and distilling it into actionable insights. Another recurring theme that comes up is forecasting. So there are lots of settings in climate change where having some kind of foresight can enable you to make a better decision up front. So for example, as we think about managing electric power grids, where at every moment power system operators need to maintain a balance between the amount of power that's put into the grid and the amount of power that's consumed, having foresight on how much renewable energy, how much solar power we expect to see produced in the near term or over a slightly longer horizon can provide power system operators with enough foresight and lead time to be able to make better decisions about how they actually balance power grids. And so nonprofits like Open Climate Fix are working with, for instance, the UK power system operator to improve their forecasts of both renewable energy and of electricity demand by taking in heterogeneous sources of data. So the past performance of, for example, solar assets, but also satellite images, satellite imagery, derived estimates of where the solar panels actually are, images of clouds that are moving in real time overhead to understand how those are going to shape the solar panels. They're ingesting all of this heterogeneous information in order to then improve the forecasts of solar power in particular going forward. And there are lots of other places in which forecasting comes up. So when forecasting the demand for public transportation in the future as an input to planning efforts, forecasting extreme events, which often takes a hybrid approach of combining, climate physics with data-driven methods. And Lynn also mentioned, understanding, for example, when locusts will pop up. So while those last two themes deal with sort of, in some sense, taking some information, historical information or large streams of data, and turning it into decision-relevant insights, there are also lots of situations in which a machine learning algorithm is actually used to real-time make decisions to actually optimize something in real time. For example, heating and cooling makes up a major portion of the emissions associated with buildings, and kind of improving the efficiency of these heating and cooling systems, because that can, as a result, have a huge impact on reducing greenhouse gas emissions. So there have started to be a lot of startups, for example, and companies popping up using machine learning to actually improve the efficiency of heating and cooling systems in commercial buildings, where the idea is that by taking in sensor data, having some information about the building's thermal characteristics, having some information about the weather, that you can more intelligently optimize your heating and cooling system using all of this data in a way that saves energy, while also kind of maintaining the thermal comfort of your building. And when we think about heating and cooling, the first thing that might jump to mind is our homes or the commercial buildings or school buildings that we're in. Heating and cooling is also a major component of what goes on in, cooling in particular is a major component of what goes on when we think about data centers and data center efficiency. So optimizing the cooling systems in data centers in order to reduce the amount of energy that they use. And this also happens in food refrigeration systems, where you want to manage the refrigeration systems in these food storage and food transportation settings in order to reduce the amount of energy that those are using, but also to prevent the wastage of food. And these kinds of optimization workflows have a lot of interactions with this idea of demand response. So how can you not only improve the efficiency, for example, of a building in its own right, but how can you think about optimizing when it actually uses energy based on the needs of the power grid? For example, if there's more renewable power available on the power grid at one time than another, that might be a better time to shift your energy demand to. So this is one kind of application that's often brought up. When thinking about optimizing real-time systems, another application area that comes up is predictive maintenance. So trying to figure out how to either ahead of time or just as it happens, pinpoint a fault in your underlying infrastructure so that you can fix it either preemptively or as quickly as possible. So you'll probably recognize this figure from Lynn's slide where she was talking about how Deutsche Bahn is basically trying to detect faults in the switching technologies in rail infrastructure in order to save money, in order to improve the reliability of rail infrastructure, and as a result make it more competitive. Another example that comes up here is the detection of methane leaks in natural gas pipelines. So as natural gas is transported from where it's extracted to where it's used, it can leak from the compressor stations and the pipelines through which it is being transported. And so using a combination of sensor data, aerial imagery, and satellite imagery, several groups have started to think about how can we actually use this to either preemptively figure out when a pipeline is going to leak and stop that leak from happening in the first place, or how can we, once a leak has occurred, actually patch that up. So while these last two areas deal with optimizing real-time operational systems in some way, there are also various ways in which machine learning can help us in some sense in forward-looking workflows, for example, accelerating the discovery of new technologies. So Lynn also showed this figure on the slide earlier, which is from a paper that is a precursor to the startup AIonics. But basically what this startup does and what this kind of area of work does is it says, let's try to analyze the outcomes of past experiments when we're trying to create a new technology in order to recommend which experiments are the best to try next. The idea here is that if you're trying to invent some kind of battery with some properties that are good for its use in electric vehicles or on power grids or so forth, how this usually works is that a scientist will sit down and say, how do I actually create a battery that has the kinds of properties that I need? Let me make some kind of hypothesis and let me actually synthesize that battery. And then after doing that, then the battery will get tested, which is something that takes several months to even a year or more to actually do. And after the results of those tests come back, you can then look at those and say, okay, what actual battery should I try to synthesize and test out next? And this design process can take a really long time because each design cycle itself, the time it takes to develop and test a battery, takes a very long time. And so what entities like AIonics do is they actually, they analyze the outcomes of past experiments to try to figure out what is the best next experiment to do, either that will give me a lot of information about the direction I should go in, or that based on the past information I have about my experiments is going to yield a good battery. And by doing that, they've actually been able to cut down on the time it takes to actually create a battery by, in some cases, 2 to even 10 times. And this kind of idea of analyzing the outcomes of past experiments to guide future experiments comes up over and over again as we think about not just batteries, but the creation of electrofuels, better catalysts for hydrogen production, and even in some cases to address various bottlenecks in nuclear fusion. And then a last major theme here is approximating time-intensive simulations. So as Lynn also brought up in her presentation, there are many situations where you might have, for example, a city planning model where you want to understand how wind is actually flowing through a city and various other things to understand the overall energy use of the city and how you should actually plan the city to reduce that energy use. Similarly, there are many time-intensive physical simulations that come up when actually modeling the climate, so in climate science, and also when we're modeling our energy systems. And in these cases, what machine learning has sometimes been used to do is approximate portions of these simulations or improve parameter estimates within some of these simulations in order to reduce the time and computational intensity of running one of these simulations, which can have a lot of various benefits. So for example, if you're thinking about planning an energy system and you're doing some kind of scenario analysis workflow where you're trying to analyze different kinds of things you can do on the system, you're often limited in the number of scenarios you can actually run because your model is so computationally intensive to run. So by potentially using machine learning to, in a data-driven way, slim down some of these models or embed information about, common redundancies or common things that can be slimmed down in these models, then you can basically increase the number of scenarios that you're running in a policy planning process. In climate science, which is related to the image shown on the slide, there are various situations in which while our climate models run at very large spatial for large spatial regions, we want to somehow get estimates at better spatial granularity in order to improve our estimates of what's going to happen in a specific city or in a specific location to allow us to make more targeted decisions. And so various works have actually tried to slim down portions of climate models in order to enable the climate models to run more quickly and, for example, allow it to run at better resolution. And so the paper pictured on the slide, for example, was trying to take one step towards this, which is trying to use machine learning to classify what type of cloud you were seeing within a particular model in order to then feed that classification result into a larger climate model that could then run more quickly because it doesn't have to fully resolve the physics of that particular cloud. So this is an overview, again, of the different kinds of ways that AI and machine learning can play into different climate change related workflows. And while it's not exhaustive, the hope is that it gives a sense of the different ways that if you work in this area, for example, your methods might play a role, or these methods might play a role in your work. Or if you're somebody who works on the methods side, the way in which your methods might, which kinds of applications or domains your methods might actually be applicable in. And while a lot of these applications are, ready for deployment today, there are also many different opportunities for innovation on the machine learning side. So for example, lots of places where we need physics-informed or robust methods in order to make sure, for example, your power grid doesn't break because you've broken some robustness property on the grid. Interpretable machine learning and uncertainty quantification are really important in scenarios where these machine learning algorithms are used to inform policy. And there are also many directions and generalization on causality and so forth. But a key point here is that the way that we develop machine learning algorithms cannot be agnostic to the applications that we care about. Arguably, even though we tend to think of a lot of machine learning algorithmic development today as pure algorithmic development, it's very driven by particular applications like computer vision and natural language processing. And as a result, the kinds of assumptions that we actually bake into our machine learning models are very tuned towards those specific applications and not necessarily meeting the demands and needs of many other applications, including those that we face in climate change. So it's really important to think about how the specific demands of a particular climate change domain actually shape requirements for how our machine learning models need to behave, and to use those insights when actually developing machine learning models in the first place. And for those who are interested in seeing a bit more depth about some of these different areas, I'd encourage you to check out the ICML 2022 tutorial that Lynn, myself, and our other climate change AI co-founder, David Rolnick, put together. And to give a really brief example, and this is Wenbo, well, let's come back to this in the Q&A, but to give a brief example of how this plays out in my own work, what my work does is basically says, how do we actually encode some of the physics and hard constraints and domain knowledge that we care about in power grids within deep learning models? And so what my work does is says, well, in a lot of these cases, we can actually write down an optimization problem that captures the kinds of physics and hard constraints that we want to incorporate. And my work provides a way to then embed those optimization problems into, for example, deep neural network architectures or the objectives that these models use to learn. So again, I'm happy to elaborate more on this in the Q&A, but for now, I'm gonna move on. So I talked earlier about various kinds of key considerations that come up in the climate change space when thinking about, in some sense, responsible climate action. And so these include thinking about climate justice, and it also includes thinking about co-benefits and interlinkages with other aspects of sustainability. Similarly, on the AI side, there's been a large discourse on responsible AI. What does it mean to actually do AI responsibly in a way that is cognizant of equity considerations, of other kinds of requirements that are needed, that we need to think about when we actually start applying AI in the real world. And a lot of these responsible AI considerations play out pretty significantly and are still very applicable to the way we think about climate action. So for example, one core aspect that we think about is how do we mitigate biases in the data and models that the data we use and the models we create? And this plays out in climate change very much so. So for example, there are many applications that try to assess the energy efficiency characteristics of buildings using data, and then use that information to actually form policies around how energy efficiency retrofits and rebates, for example, should be targeted. But it's important to realize that these large streams of data about buildings encode our histories of housing discrimination, of uneven access to capital among different populations. And as a result, those historical inequities are going to show up in any analyses, large-scale analyses that we do on that data. And so this is very important to be cognizant of in AI and machine learning workflows, where in some sense, you're putting a large amount of data into these algorithms to make these analyses. These algorithms are going to pick up those biases that are inherent in the data. And so it's important in the way that we actually frame the data and frame the problem that we're very much aware of this. Similarly, data about buildings is unevenly available across geographies. And so training a machine learning model to identify building energy efficiency characteristics might then end up working well in some geographies and not others where there's less data. So it's just important to be cognizant of these kinds of considerations. Similarly, the way we develop our models also can embed various kinds of biases that we as the designers of the algorithms might have. So for example, when weather and climate models are designed, they're usually designed by writing down some kinds of physical rules. But those physical rules might be slightly off. They might diverge slightly from what we actually see in the real world. And so one process of the model development process, or one part of the model development process, is calibration, actually figuring out how to readjust the model so that it actually fits what we see in the real world. But what we often see, for example, in the development of weather models, is that the calibration is done with a particular region in mind. So for example, ECMWF does weather modeling for Europe, but the data that they actually calibrate their models on is then, they have more data in Europe, so that's what they calibrate on. And as a result, the model does not necessarily do as well in certain other regions, and in particular doesn't do as well in Arctic regions, where the actual way the Earth is even gridded breaks down because our grid squares are too small at the poles, and they don't reflect what the grid squares look like in the middle of the Earth. And so the data representation, the calibration, these many different things encode biases in that we as algorithmic designers might have. And again, it's very important to think about that. Another kind of big axis of responsible AI is improving trustworthiness and accountability. So for example, in power grids and industrial operations, thinking about safety and robustness is very important to make sure that you don't break these systems. And interpretability and auditability becomes very critical in, for example, policymaking contexts. It's also very important to center equity and climate justice in various ways. And this means doing things like centering diverse stakeholders, even in cases where those stakeholders are not going to be, your research funders. So for example, there are a lot of collaborations between industrial agriculture and academia because industrial agriculture has the funding to fund that research. But smallholder farmers don't tend to have that large-scale funding infrastructure to fund academic research. And it means that a lot of the agricultural research in academia, including in machine learning and robotics, tends to favor problems that are geared towards industrial agriculture rather than smallholder farmers. So again, being cognizant of these effects and figuring out how to break these effects is very important. Similarly, AI and machine learning technologies are often very expertise intensive, compute intensive to actually create and run, and not everyone has access to these kinds of resources. So figuring out how to deal with that and how to not centralize power by virtue of who is able to actually run and develop algorithms is very important. And another effect to be aware of is avoiding something called digital colonialism, basically a scenario in which, as we start to see large streams of data available, for example, in developing countries, making sure that those of us in developed countries don't, in some sense, exploit this data in ways that then those populations see no benefit from and are not included in the development of. So, for example, this occurs when we have a lot of satellite imagery. There's a temptation to sit in the US, for example, and really analyze outcomes using satellite imagery for another country. And this often happens without the involvement of those who are on the ground in that country, who understand the considerations inherent to various kinds of scenarios in that country. And that is something definitely to not do, to avoid, even though we have this kind of global scale data. On the ground knowledge, of course, very critical to take into account. And similarly, we start to see smart meter data from power grids being available in a large variety of geographies, but some places like Europe have much stricter protections over this data than other places like India. So it's important not to, in some sense, take advantage of the differences in individual privacy protections in order to just then say, oh, this is a convenient data set for research, but it's important to really think through the implications of that. So a last few considerations and caveats. So we're in this, section, I really talked about, where AI and machine learning can play a role in climate action, but it's worth noting AI and machine learning are not silver bullets. They are not needed in every single climate strategy. And where they are applicable, they're only one part of the broader strategy. In addition, impactful applications of AI and machine learning may not be flashy. Think, for example, detecting switch faults in rail. These can still be very impactful. And it's not a substitute for careful problem framing. AI and machine learning will inherit all of the biases and misframings associated with a particular problem and just amplify those. So if you're running a power market and you're using AI and machine learning to optimize your power market, if your power market is not solving for the right things, your AI and machine learning algorithms are not going to fix that for you. And in fact, they're potentially going to amplify those issues in your market design. And there are also various considerations to think about for deployment. As Felix mentioned in the very first talk, in some ways, a lot of the technologies that we need are already there, but a lot of the issue is that we don't have these pathways to deployment to actually actualize these technologies. So as you're doing this work, understanding, priming, and enacting this pathway to deployment is really important, noting that sometimes simple methods work very well, and sometimes you have to be aware of things like rebound effects, as Lynn talked about in her talk. Thinking about equity and ownership and access, as I talked about before, is also really important. So thinking about if I create a particular technology, AI machine learning technology, who's going to be able to use it, who's going to be able to participate in actually shaping it, and how should that affect the way I approach this in the first place. And as a result, partnerships among multiple kinds of stakeholders are key. So researchers, implementing industries and end users, policymakers, and other affected parties. So that's my overview of this topic of AI for climate action. And for those who are interested in learning more, I'd encourage you to check out the original Tackling Climate Change with Machine Learning paper. I also have a review paper out that deep dives into sustainable energy system applications in particular. And as Lynn referenced, there's this report for the Global Partnership on AI, which talks about what policymakers and international organizations can do. And in general, for those who are interested in thinking more about these applications of AI and machine learning to climate action, or this broader picture on how machine learning and climate change are related, I'd encourage you to check out the Climate Change AI Initiative, which Lynn, myself, and others have co-founded. So through the Climate Change AI Initiative, we provide various kinds of resources, kind of framing the relationship between AI and climate change, both reports, but also summaries, tutorials, a wiki, and things like this. We also have various conferences and events. So for example, a series of workshops at the major machine learning conferences, events at the UN Climate Change Conference, a summer school where you can actually seek education and meet others in this area, and also mentorship programs where we match those who are maybe submitting to our workshops with experts in this area. We also provide various kinds of funding and grants programs for researchers, have an online community platform and a newsletter where you can meet others and learn more about calls for submissions, jobs, readings, and other things ongoing in this area. And also webinars and virtual happy hours where, again, you can learn about ongoing developments in the area and meet others. So if you're interested in diving further into these areas and meeting other like-minded people, I'd encourage you to check these things out by either going to the Climate Change AI website or feel free to contact me as well. So with that, thanks so much for listening, and I look forward to your questions and further discussion.
Thank you for the talk, Priya. That's really informative, I believe, for a lot of people. Questions? Wenbo?
Yeah, I have questions, but I would like to wait until if there's some other audience have the questions.
Sounds good.
Any questions from the other audience? Yeah, here you go.
Yeah, Hussein, please go for it.
Hussein, you can unmute yourself and ask a question.
Oh, thank you. Can everyone hear me?
Yes.
Yeah.
I have a quick question. At what point would you say that AI or machine learning becomes more harmful to the environment and climate change than it is helpful? And what do you think developers should keep in the back of their mind when creating AI to ensure they don't begin to sway into that harmful area?
Yeah, that's a great question. So I think there are a couple of axes of potential harms to think about. So one of these is, of course, the emissions impact of developing the model in the first place. The other is thinking about, who has access to various technologies or is able to actually then participate in development. And then, various kinds of the things I mentioned about, biases, inequities, and so forth. In a lot of these cases, I would say it's not a matter of whether the harm outweighs the good, but rather that these things are abundantly shapeable. It's very, very possible to develop your AI or machine learning workflow in a way that does not exacerbate inequities or actually explicitly counteracts various kinds of inequities. So for example, in a different area of policing, there are various initiatives that use AI and machine learning to predict where police resources should be allocated, which have been, by the community really talked about as this really exacerbates inequities. But then other people have turned that around and said, well, can we use AI and machine learning to actually predict when police officers are going to misbehave? And that in some sense turns the paradigm around, and it turns the narrative of power around and uses AI and machine learning to actually help the more vulnerable people in that scenario rather than helping those that already have power. So for these kinds of effects, I would say it's not a matter of agnostically, like, am I doing a certain amount of harm and have I reached a threshold? But it's really thinking about how do I shape what I even work on or the way I work on it in ways that lean into actually addressing these power dynamics issues and these equity issues rather than exacerbating them. When it comes to the emissions portion itself, I would say that this is something that it's funnily, we think about it less in academia, but it's thought about very commonly in industry, where in industry, right, it takes more resources and more emissions and more compute costs to actually develop a really large model. And if the epsilon increase in accuracy isn't actually improving your bottom line, actually many companies won't even go about doing that. Which is to say, in some sense, implicitly, these trade-offs are already being made, but they need to be made more broadly, because in general, this idea of what is the benefit of an application, as Lynn said, are we going to, is it going to save tons more lives to have this small more amount accuracy in the model, which creates more emissions? Maybe it's worth it in that case, but if it's not worth it, then we shouldn't incur those emissions. And there are lots of value judgments associated with that, because, for example, emissions and lives are not in the same units, but nonetheless, these are the kinds of trade-offs that we need to think about. So yeah, so the takeaway there is I don't think it's about there's a harm budget that we hit after which it's bad to keep going, but I think it's really about internalizing these kinds of considerations when we're actually framing and shaping what we work on in the first place.
Okay, thank you so much.
Any other questions?
Yeah, okay. So yeah, so okay, my turn. Yeah, actually I have 2 questions, and yeah, very interesting presentations. And yeah. So my first question is regarding the calibration procedure. So actually we had the similar issues in our research on the topics about the calibration versus the design optimization, because you know that the end goal of those calibrating a simulation model is kind of like to use this one to guide a better design or better decision making. So it's mainly relies on how you predict the responses from the system responses, not only the simulation, meaning that you need to calibrate the model first and then get a good prediction, then do the decision making at the very end. So, however, we heard from the our intuition from the model calibration community is that they care more about the scientific interpretation of the calibration procedure, especially if there are some like models simulation model parameters. They care about like the procedure of identifying those parameters, how to define the parameters and how to make good predictions. So I'm just curious about like in your field, what is the trade-off between these two? Because sometimes if you want to achieve a very good estimation of the parameters, then probably going to sacrifice some of the prediction performance in your prediction model, and then that's going to bias your decision making procedure, right? And that's also highly dependent on your sample size. So.
Yeah, it's a great observation. And it's one that also comes up when thinking about, like, people often ask, what's the distinction between machine learning and statistics? And the real distinction is that the statistics community cares about creating unbiased estimates of parameters and models, and the machine learning community cares about the performance of the output of the models more so. And so I think it's one of those things where different communities will just end up using these methods and developing these methods with different aims in mind. And I don't necessarily have a good solution to sort of, merging the cultures is not necessarily a solution, but just being cognizant that, when you do it with an applications perspective, you're just going to end up pursuing it a bit differently than somebody who's pursuing it from a statistics perspective. Unfortunately, nothing more insightful to say than that.
Yeah, thank you. So the second question is on the role of the AI played in this field, because like I work on this one. I think most of the methods mainly focus on like the Gaussian process, like kriging, stochastic kriging, and then plus some like Bayesian or like Bayesian sampling techniques, right? So like I think like recently like AI stepped into our horizon, saying that probably we can use some AI to make some prediction. However, I know that there are some techniques for the sort of quantification on AI, but it's still not widely adapted, to our design. That's one question. The other question is that it's about the constraint on the sample size, because you also mentioned that there could be different sites that need different strategies of calibration. So if you divide it into those subgroups, so definitely we're going to make more direct or scientific contributions to the local community, but it's going to also give us a smaller sample size. I mean, in the stat field, it's okay because we do Bayesian, we have the statistical power, so we know what is uncertainty, and we know that what we should know. But in AI, if the sample size is small, then probably it's very hard for us to train a good neural networks for the model discrepancy and also the estimates. So like, what is our strategy on this topic?
Yeah, so there's definitely a lot of different work going into this, and I'm not going to pretend to provide a perspective on all of the work that's going on in this area, but let me tell you a bit about what I'm doing here. So I talked about this framework that my work adopts called optimization in the loop AI. And again, the idea is that we want to basically develop methods where we have some kind of encoding of our underlying physics, be it like we have an optimization problem that captures some of the physics that we care about, or captures some of the constraints that we care about, or an ODE or PDE or something that captures some aspects of the dynamical systems that we care about. And we actually want to figure out how to embed those within deep learning models. And so what my work does is actually tell you, how do you actually embed this into a deep learning model? So imagine you have this like machine learning model where X are the inputs to the model, you have some outputs, it's being evaluated on something, and your model is a neural network. Well, you can think of a neural network really as just a bunch of nonlinear functions with parameters that are composed together. And so and where the parameters are updated using back propagation. So where you're taking some gradient or derivative of the loss function with respect to your parameters. And so the idea is, if I can tell you how to create your ODE or your optimization constraint in a way such that I know how to take derivatives through it, then it's compatible with being embedded into this deep learning workflow. And so what my work does is say, can you actually create a neural network layer that in my case represents an optimization problem, but in other cases can represent other kinds of physical constraints? And using that tool, you can do a lot of different things to actually merge between this data-driven process where your neural network, for example, is taking in data and learning something, but embedding some inherent notion of the physics that you already know about. And this can both improve, various kinds of generalization and performance, because you're now taking into account both what your data can tell you, but also what your data can't tell you. But it also actually, in many cases, improves sample efficiency, over or like data efficiency over a pure data-driven method because your physics is providing enough of a prior that you don't necessarily need as much data as you would have needed before with a pure neural network method. So happy to go into even more detail, maybe offline, on how this actually works, but this is the basic idea. And the keywords to look up are optimization layers or implicit layers on this broader set of literature.
Thank you. This is a great idea. Like, yeah, I feel like you are trying to, like, I mean, in the previous literature, most of people just treat the whole simulation model as a black box. So I think what you are trying to do is that make it a little bit like a gray box and make use of the actually. Yeah, that's a great idea.
Yeah.
Thanks.
Yeah.
Thanks for the answer.
I think there has been some work in making some kind of like parameterized functions. It's this sort of like that, where it's more of a parameterized function and then figuring out the parameters, or it's like a convex neural networks. I think there was
like input convex neural networks. Yeah. So there's a couple of ways you can do this. You can have your optimization layer be like an optimization problem that has some free parameters in it that you're trying to learn. And this might be a situation in which you have some kind of data, you're trying to, you have some physical equations, you don't know the parameters of those physical equations, your data can help you learn about those and you go forth. But there are other situations where you might have like a decision-making problem or a physical problem that you know all the parameters of. You're not trying to learn anything about that problem, but you just want your neural network to enforce it. And so in those cases, your optimization layer like would not have any free parameters. So it can be, it's related to this area, like this learning the parameters of something is one use case of this. But more broadly, it can just be used to embed these kinds of known optimization problems as well.
Sorry, my kid was screaming in the background. One question I want to get a little bit away from this. You talked about biases, and I was reading Timnit Gebru's paper for the famous one,
the stochastic parrots one.
Yes, and also the other one that caught my attention was a report that came out on University of Chicago researchers who have claimed to predict 95% of the crimes occurring, and they're just like all sorts of alarm bells go off. What kind of crimes, how do you predict, are those actually crimes, those kind of questions, right? Because historically judicial data again is riddled with errors. So that was also that got me thinking, how do you're talking about centering equity and climate justice, and again I'm thinking from a point of view of we as researchers in the university sitting and working on it. How do we bring these kind of, first, how do we avoid biases, right? And the next thing, if there are biases, how can we correct them in neural networks?
Yeah, that's a great question. So one important aspect of this is working with a broad set of stakeholders. So one thing that often happens when you think about, let's use that case study of a predictive policing algorithm. A lot of the researchers there will say, awesome, so we're researchers and we're working closely with the implementing industry, which is the police force, and the end user, which are the police officers. But then there are these other entities to think about. So who is affected by the use of a predictive policing algorithm? It's not just the people who are actually implementing it, it's the people who it's going to be used on. Or it's the policymakers who will be, thinking about, what are the macro, how does this fit in on a macro scale? So I think it's basically about not forgetting to include some of these other parties that are not directly on your implementation pathway, but nonetheless are affected by or should have some say in how the technology is implemented. So that's one. But the other one is, I think, like looking to work with stakeholders who are not the immediately obvious stakeholders. So not, like I was mentioning this earlier, right? Not the ones that happen to have a ton of funding for your research, right? But like write an NSF grant with a smallholder farmer, right? There's some aspect of breaking out of certain patterns of convenience, because these patterns of convenience is what leads us to work with large scale image and text data that can be scraped from the web because it's convenient, because the players that can actually create that data are doing that really easily. And I think we can basically, it's not easy, right? It's not like, oh, okay, take a right, go to the job fair, take a right, and there are all the people with money, and take a left, and are all these other stakeholders you can work with. It takes some amount of personal investment, but I would say it's very important personal investment to make, to really just think about a different set of stakeholders whose problems you're solving, and not always those in power or with money.
Yeah, I think that's a very important message to get across as well. So thank you for that.